Thank you for joining my talk. In this talk, I'm going to introduce how we change InnoDB to make it possible to run multiple instances based on same copy of data files and local files, so then we can easily extend the readability. Before the talk, I assume that you all have a basic understanding of InnoDB's interface. For example, you know how InnoDB implement MVCC, how InnoDB manage its local files and data files. And I have uploaded this slide to the website of Percona. You can download the slide from there right now. Okay. A quick introduction to me. My name is Zhai Weixiang, and I joined in Alibaba in the year of 2011 after I graduated from school, and has been working on MySQL since then. And I'm currently working at Alibaba's cloud service department, and my work is mainly focusing on InnoDB. So if you have any question about this talk, you can send me an email or contact me from Facebook page or tweet or from Twitter. Okay. So in this talk, firstly, I introduce some traditional ways to scale out read, and then I introduce the new replication architecture, and after that, I introduce how we solve some key issues while implementing this feature. Okay, so the first way to scale out read is if your system is completely read-only. For example, after loading your dataset to the server, you can guarantee that you won't change the data anymore. Or if the dataset is persisted on a read-only media, you can turn on InnoDB read-only. While this option is turned on, the server will not acquire the exclusive file lock while opening a table space. So then you can run multiple instances based on same copy of data. And but as you see, you have to guarantee that your whole system is completely read-only. So this means you can't use this method in general scenarios. And this is another way to extend the readability, and it's also the most popular way. And if your system can tolerate some a replication delay on slave, then you can distribute your read workload to slave and read data from there. And if one slave is not enough, you can keep adding more slaves. Mostly, your readability can be increased linearly. Okay, but adding a new extending read by adding new slave is first, it's very time-consuming, and it occupies more disk spaces. And most time you may need to make a full backup from a running master server, and you need to restore a full copy of data to a new server. That may need a lot of time, and there may be some accumulated binary logs while you are restoring the new instance, so you need to replace the delayed logs. And sometimes the select queries on slave may be sensitive to replication delay, but as we know, the binary replication is not so effective. For example, if there is a long time running transactions on master and it changes a lot of records, or if there's a long running DDL on master, then replication delays. And at last, it may slow down the master server if there are too many dump requests. There will be more matrix contention and will occupy more bandwidth of network. So, in order to keep away from these issues, we need to provide the ability to first we have to we need to start a new read-only instance without copying data from master. So this should be very fast. And the new instance can provide service in less than 1 minute. Okay, that's my boss requirement. But we can do this in most cases. But that also depends on the real scenario. And at last, the master server can still provide all kinds of workloads that a normal MySQL allows. So how to make it workable? First, we have a nice code base. It's a heavily modified storage InnoDB storage engine. We changed the InnoDB to let it support physical replication. You can find the slide by this link. I shared physical replication at last year's Percona Live, but at a much smaller room upstairs. Okay. And with the physical replication, we can easily change the code to make use of read to log. So we can update the cache of the read-only node by replaying read to log, and we can, and exactly we can make use of shared storage. Okay, but it's not so easy in real life, because as we know, most shared storage are provided as a raw disk. So we have a team that is working on a simple file system. Maybe next year I will share that, but it's still in process. And besides, NFS and net file system also always is also workable. So with shared storage, we will set the data directory to same place and run multiple instances based on same copy of data and read files. Okay. So this is the overview of the new architecture. And here there are three kinds of instances. The primary server provides all kinds of workload, and in another region we always set up a standby, which has have a full copy of data and log. And between primary and standby, we use physical replication. The primary server will ship read to log to standby, and standby use read to log to update its local data. And in region 1, in the same region, we can deploy multiple instances. We call them replica. It's completely read only, and it shares state and log with the primary. And each replica will collect to primary, and they will keep communicating with each other and exchange state. Okay, here is a summary what a replica is. It only affords read-only ability, and and then the statement, if you execute a statement on replica that may change the underlying date, it will be rejected, and an error will be thrown out. And it shares log and data files with the primary server. Because it doesn't modify any physical files, it doesn't need to maintain a flash list or buffer pool. And at last, all data files are open in read-only mode, and it skips acquiring exclusive file level lock. So, and that makes it possible to run multiple instances based on same copy of data. Okay, here is a more detailed view with all involved threads. First, each instance has 2 threads, and they will keep communicating with each other. So why do we need 2 threads? That's because when one thread sends information to another instance, we don't want another instance will want to send a message to the first one. So we don't want to block each other. And on primary server, we filtered how transaction is committed. While a transaction is committed, it will be added a query, and we added a thread called LGWR, which will help other threads to writing and fsync redo log. This will improve the performance while under heavy workload. And after writing log to share storage, it will wake up the message sender thread, and the message sender thread will tell the replica where log has been written up to. Actually, the latest everything will be sent to replica, and also some other messages that I will introduce later. Okay, so on replica, the message receiver thread will wake up the log parser thread, and then the log parser thread will read the log from the shared storage, and pass the log and store pass the log to hash table. And beside the log parser thread, we create a multiple worker thread, so we can apply redo log in parallel. And the worker thread will get the log from hash table and update the buffer pool. Okay, and on primary server, there is a page cleaner thread which is responsible for flashing dirty pages. So from the picture, we can see that the replica may be reading data from shared storage, while the primary server is writing dirty pages to the disk. So, okay. So, in order to make the new architecture workable, we have to solve some key issues. The first problem is we need to control how page is flashed on primary and how page is invited on replica. Because as we know, the B tree of InnoDB organizes its state by using B tree. So it's structure. So, but InnoDB uses a WL strategy, which is called write after log. So, which means if you access the data on disk directly, you may read B tree which is broken. So, okay. So this is the first issue. The second issue is we have to start provided the ability to start a replica instance while the primary is actively modifying the date on disk. And we also need to support MVCC on replica, which means we need to know which data is which transition is committed, which a lot, and also how to control the undo purging process. And besides that, we need to reply DDR on replica, which means while the B-tree structure is being changed on primary, we also need to make sure that the table space is not accessed by any replica. And at last, we need to provide the ability to switch between primary and replica. We need to support the failover. So if the primary is down, we can quickly promote replica to a primary server. Okay. Okay. So first problem is we need to avoid reading a page from replica which is being modified by primary, which means if a page is actively updated by primary, the replica at the same time the replica reads this page into its buffer pool, it will consider this page as a corruption one and then throw in a serious error. So we must avoid this situation. The second problem is because B-tree is structured, we need to avoid reading pages in future or in past. So what's that mean? This is an example. So after we insert some record, inserting some record to page 3, it may get to 4 and then beneath into two page. And after that, the page 1 is updated and add a new node pointer which points to page 4. So if the page cleaner thread flashes page 1 to the data file before flashing other pages, then and on replica, a user client wanted to access will read page 4 into its buffer pool and then try to access page will read the page 1 into buffer pool and then try to access page 4, which hasn't been initialized on disk. So some errors will happen, and we should avoid this. Okay. So let's make some rules. First, the replica will always apply all logs in memory, no matter if the target page is in memory or not. So we can keep a consistent stream in buffer pool. And secondly, the primary instance has to make sure that the page has been read into buffer pool or replicas before flashing its dirt changes to disk. So we can avoid partial reading. At last, the replica instance only allows to invite pages that when the copy in memory is the same as the copy on disk. Okay. Here is a basic algorithm. So So in order to flash a page on primary, it will first need check if the first modification on this page is smaller than or replicas applied everything, which means the first modification has been applied on all replicas. So we can guarantee that the page has been read into buffer pool or replica. And after the page is flashed to disk, the latest areas on the block combined with its page number will be stored and later transmitted to all replicas. And on all replica, before inviting a page from buffer pool, so it will first check if the page is clean or not. If clean, then we can invite it from buffer pool. If not, then if not, then we have to make sure that it equals to the block everything on disk. If yes, we can invite it. Here is an example. We firstly modify a page at everything 10, and then secondly modify the page at everything 20. After that, we want to flash page to disk. It can't be flashed to disk if the applied everything or replica is smaller than 10, because the first modification hasn't been applied. We don't know if the page is in buffer or not. And after that, the page can be flashed to disk. And on replica, if the applied everything is smaller than 10, that means the page is clean, so we can invite it. And before it's flashed on primary, it cannot be invited from buffer pool because it's possible that the page is being modified if we invite it from buffer or replica, and later a user's client may read it from disk, which so there will be a configuration. Okay, and after flash it down, we can be sure that the page on buffer pool has the same error thing on disk, which is 20. So, but there's a drawback of this method because the page flash on primary will be affected by the replication delay. And we have two ways to solve this problem. Firstly, we can configure a threshold. If the delayed sequence exceeds this value, we will kick out this replica. And besides, we did some work to optimizing the performance of replicating. First, we can apply logs in parallel. We create multiple worker threads to apply log, and after passing the log, its log entry is distributed by based on space ID page number. Okay, and the second way is according to the layout of current return log format, it requires two passing it requires two passing of a simple a separate log entry. The first passing is to check if the log is corrupted and find the end position of the log of this log record. And after that, this log will be copied to hash table. and it will be passed again while applying this log entry. But we can omit the first passing by storing the length of this log entry in the header, in the log header. This will greatly improve the performance of crash recovery, as I reported in this backtick. It's verified, but I don't know when it will be fixed. Okay. And the third way is InnoDB, while replaying some kinds of redo log, it needs to create a structure called dummy index, and also with a dummy table to help replying log types such as inserting a record into page or update a record on page. So this is time consuming, but the dummy index doesn't store too many meaningful things. It only relates if the data change if the index has same number of fields that have same number of fields or like the dummy index, then this dummy index can be reused. And so in order to fix this problem, we create a cache for each log apply thread, and the dummy index will be cached in local after it's been created and then be reused. This really saved a lot of CPU times, and we can see great improvement on while testing this. And this bug also verified long time ago. Okay. So while studying a replica on fly, the primary server may still have some dirty pages in buffer port that hadn't been flashed to disk. But as I introduced before, we can't access the disk directly because we may access a broken B tree. So we need to rebuild these pages in the buffer port of the replica, and then after that, only after that we can accept requests from user clients. First, it will before initializing the interdictionary system of InnoDB, it firstly collects two primary. It will optionally make a checkpoint, so there will be less dirty pages in buffer port, and if we made a checkpoint, then the simulated crash recovery or replica will be much more faster. And after that, it will register a memory object on primary and takes the order block arraying in buffer port as the initial value of the applied arraying on this new replica. And after registering this new replica, the primary server is the page flashing on primary server is subject to this new replica. Okay, and after that, it sends the first packet to the new replica, which includes the oldest arraying buffer port as the initial value of applied arraying on replica, and the newest arraying, which means after applying up to this position, reader is safe. And also the snapshot of global transaction state while taking the value of newest modification, newest everything, and the log file information, which include the log file size and everything, and its file offset. So with this information, we can calculate the file offset by providing everything. Okay. So with this information, the news replica will start reading log from all the everything, and then apply log up to the newest everything, and then overwrite its global transaction state by the snapshot copied from primary. And after that, it's safe to initialize other components, and after that, start accepting user requests. Okay, so after starting up a replica, they will keep communicating with each other. The primary server will keep sending the latest log everything on disk, and also the state, which include which page is flashed to disk and the everything of this page. And the replica will send back the log everything that has been applied up to, and also the order read view for undo purging purpose control. Okay, MCC on replica. So on primary, as well, when we start read-write transaction, it will assign a new transaction ID, and then put the transaction ID into a global IDs array with the transaction sys prefix. And while opening a read view, it will copy the global transaction IDs array into local. So while processing this query, it loads which date is visible or not. If a record is on table space is not visible, it will tracking the older version of this record by from undo table space to build a consistent snapshot. But on replica, we need to provide some ways to track which transaction is committed, which are not, and we have to. It shouldn't see any. Shouldn't see the date which is not committed on primary, and we need to control the purge operation on primary. It shouldn't clear the undo log if the log may undo log may still be referenced by any queries on any replica. Okay, so in order to resurrect the transaction state on replica, there are two steps. The first step is initiate the transaction state by copying that from primary during the simulated crash recovery. And after that, it will update the transaction IDs array via redo log. We added two kinds of redo log. The first is the mlog transaction start, which marks the start point of read-write transaction while it started and assigning a transaction ID is logged in order. And another log is mlog transition commit, which marks the endpoint of a transaction after marking undo state as committed. Okay, here is an example. The initial master transaction ID is 11, and the first batch of log consists of 2 transactions. It starts transaction 11, 12, and commit 11. So we updated the global transition state after applying 1 batch of log, and after that, the master transaction ID is 13, and when we add a new uncommitted transaction 12 to the set. The second batch we started transaction 13. So the same way it's added to the transaction ID array and advance the max transaction ID. And also So okay. So in auto control, the which undo log could be purged on primary. Firstly, every replica will keep sending the oldest reader view to the primary server, and then the purge thread on primary server will create a snapshot for purge based on the oldest view or oldest reader view on primary, and all reader views shipped from replicas. So it will guarantee that any log that be referenced by any active reader view inside the cluster will not be purged. But the drawback of this way is that undo table space may grow extremely large. If there are any long-running transactions on replica. So, but luckily, in MySQL 5.7, we can truncate undo table space online, which is a very useful feature. Okay. While a table space while the structure of a table space is being changed on primary, mostly this table shouldn't be touched by any user clients. On primary, we can guarantee this because there is the MDR lock on this table while the DDR is running. So on replica, because the data file is shared on shared storage, so every file name changes will be visible to all replicas. So we have to make sure that the user client replica will not access this table while it's been changed. So we add 2 kinds of redo log, which the first one is the mlog met change start, which is written to redo log after acquiring an exclusive MDR lock on primary. And another log is mlog met change end, which is written before releasing exclusive MDR lock. And besides this, we consider DDR as a synchronous operation, which means the MDR exclusive lock should be acquired on all replicas before the primary starts creating, deleting, or renaming IPT file. Okay. Fail over. So exception always happen. But we always think kinds of ways to reduce the downtime. we have to allow a replica load to take over quickly if the primary load is found to be offline or unreachable. So mostly we deploy the replica in the same region of where the primary server resides in. So if the primary is down, we can promote a replica to primary. This can promise low data loss, and if the whole data center is down, a standby will be promoted to primary. We implemented something similar to semi-sync. So if we enable a synchronous replication, we can promise no data loss. This is the main steps to promote a replica to primary. First step is to promote replica to standby. It will reopen all data files in read-write mode and check if the block is if any block is corrupted by traversing double write buffer. And after that, it will write the dirty blocks to disk by scanning its area list. And after that, it will check the redo log on disk and find out the latest area thing, the area thing of last redo log, and then change state to primary, and change state to standby. So they shares the replica and the standby shares the second part of code, and on standby it will apply all logs up to let's say everything, and change the server state to primary. And after that, it will need to reinitialize some in-memory objects such as a rollback segment, change buffer, and some other things. And then it will roll back or it to resurrect uncommitted transaction list and do some cleanup and roll back uncommitted transactions. And after that, it will make a checkpoint and start accepting read-write workload. Okay, thank you. And the rest in time, this works and start our public branch on GitHub. And next talk at this room is from our college, and his talk is about flashback, and which is also called the time machine in InnoDB, in MariaDB. Okay, that's all. Any question? Yeah. It's not open source yet, but we are open source this project later while it's production ready.
Yeah, you have the slides.
Yeah, I have. Yeah, you can find that from the website of Percona Live.
Okay.
Yeah.
Which version of InnoDB do you actually officially support?
Yeah, actually, currently, we develop this feature based on 5.6, but I'm working on porting this feature to 5.7. But that's a big project, and MySQL 5.7 have changed a lot of things, so that's very terrible.
Right now it's only available in RDC, not the channel.
Yeah, yeah, but maybe later we hope we can contribute in this project to other branches. Yeah.
So the code is already in the GitHub, right?
It's not yet because it's not production ready. We periodically release our patches to this GitHub every month, but because this feature is under developing, and actually we hope we will release this the code after it's production ready. Actually, after running on our production, when we confirm that it's stable enough. Yeah, on cloud. Yeah.
I have a question too.
Okay.
Have you done any benchmarks to evaluate the overhead of communication between replicas and the primary? Can it become a bottleneck if you have too many busy replicas? Then the overhead of talking to can it become a bottleneck?
So if there are too many replicas,
they're busy. Like there's, as I understand, MVCC information is communicated back from replica to primary, right?
Yeah.
To keep purge from deleting.
So if there are too many replicas, then then the overhead for calculating the read view is very heavy. So this is work is still in process. I hope I can reduce the overhead, but it's in process. Yeah. Any question? Thank you.